It's time to get started. So our next speaker is Professor Igor Frenkel from Yale University. The title of his talk is Programs in Representation Theory.
Thank you very much. Yes, it works very well. So thank you for the introduction, and I would like to thank the organizers for inviting me to this celebration of mathematics, physics, and other sciences that I don't even know. All right, so my talk is titled Programs in Representation Theory, but on the other hand, S can be omitted. But then it becomes not so clear. So it's split into many small programs. Each of them is quite realistic. Many of them are known, but I would like to say maybe something new, at least at the end. All right, so everybody in this room probably knows what representation theory of groups is and why it's important. I just can say that, first of all, it's related to analysis. For example, for compact groups, it's essentially the same thing. And Lie groups also related to algebra and geometry. And this field kind of cuts across all mathematics and has enormous applications to physics, like representations of Lorentz group, Heisenberg group, unitary symmetry. So already were used, and we might expect that even more representation theory will be used in physics as soon as we'll discover this. So now about programs in representation theory, there are natural programs, just study new or old groups or new or old representations. And well-known programs, unitary representation of, say, real simple group or group over finite field by George Lustig, or automorphic representations. So, but these problems are really very difficult. To advance them, you have to be the Vaughan or Lustig or Langlands. So the programs I propose is kind of much easier. So it's at the level of graduate student that you can go home and write a paper in a couple months, and it's quite realistic. So all these programs that I want to discuss, in fact, generalization of classical representation theory. So, and my main motivation is the future of representation theory with applications again to mathematics and physics. So what is classical representation theory that I have in mind? I believe it's more or less coincides with everybody else's point of view. And we've seen in the talk of George Lustig that he mentioned, for example, classification of simple Lie groups. So G will be denoted compact group, and GC, its complexification and corresponding algebras. So that classification theorem he considered as one of the greatest achievements, and I agree with him. So, and then second thing is classification of finite dimensional reducible representations that also kind of figured in his talk, which was done by Cartan. And then a little later, character formula was found by Hermann Weyl. But character formula only, while character formula only exists for the subalgebra of G, which is so-called Cartan subalgebra. If you think about G, main example as SUN, so this is a diagonal matrices. So this formula has a generalization which was done by Harishchandra, who expressed character in arbitrary reducible representation V lambda of any element of Lie algebra group. So in terms of the integral of orbit, which is a Flach variety or degeneration of Flach variety. So that's some ABC of representation theory, and maybe a little bit more. So we can add to classical representation theory Peter-Weyl decomposition, Borel-Weil realization of reducible representations, and maybe a very important step, Serre's realization in terms of generators and the relations of simple Lie algebra using Cartan matrix or Dynkin diagram, which is some kind of DNA of the Lie algebra. So you can add to this. So Serre result appeared in 1966, and classical representation theory I consider as being kind of essentially accomplished in the first 2/3 of 20th century. The whole representation theory is relatively a recent development in mathematics in comparison with, say, Pythagoras. So it's just the end of 19th century. Yes, the 19th century. So it's 2/3 of 20th century is classical representation theory. However, you can add few more results which go beyond, which still have this invariant flavor, like Bernstein-Gelfand resolution in category O, which is slightly larger than category containing irreducible representations. One can also, so in principle, you can extend it the way you like even. And in particular, you can add representation theory of split real forms, like principal series, just the simplest part, which has similar structure to that. So then, yes, the first program that I want to discuss, and the first generalization, is based on Serre relations. So he used kind of ordinary Dynkin diagrams which don't contain 0 point, but it was the natural idea developed by Katz and Moody to extend it to more general graph, the construction of Serre. In particular, there is a natural class of Dynkin diagrams extending ordinary Dynkin diagrams just by one extra vertex and corresponding edges. And then this is, yes, no, opposite direction. Yes, so that was done by Katz and Moody in general, but for extended Dynkin diagram, it's especially interesting because you have realization of these algebras as certain infinite dimensional Lie algebras. So that was the first step of affinization in 67, but at that time it was not immediately appreciated. So it took another 5 years, and before some fantastic paper of MacDonald appeared in 1972, which I considered affinization of denominator identity. So Weil group was replaced by a affine Weil group corresponding to this affine Lie algebra, and this identity has been proven. It was not absolutely straightforward because you have to use some fact that sum of natural numbers is equal to -112. But if you do it carefully, then everything works beautifully, and then you get this affinization. So McDonald probably did not know about Katz-Moody result, but together, after these two results appeared, it was clear to everybody that there is enormous new direction. The only thing that not everybody had tools to generalize highest weight models. It was done by Katz, and he also found generalization, affinization of Weil character formulas. So I immigrated in '79 to the United States, and I already was quite aware about this affinization program, and I was exactly in such a position that I needed some paper. I just went at home, as I said, and consider affinization of Harishchandra formula. So this worked extremely well, but now you have infinite dimensional orbit, which is equivalent to all possible paths from identity element to conjugacy class on the group. And you need to integrate over infinite dimensional measure, but just formal algebraic expression just indicated that it should be Wiener measure. And when you integrate over Wiener measure, you get precisely the correct character formula by Katz. So that's an example of affinization. There are many other examples. And still, this area is not completely closed. But also, besides straightforward generalization, some unexpected structures appeared. So one of them is vertex operator algebra. I do not want to talk about the full history of this. I gave an interview where I explained all this directly. So, but in this case, you have certain generating function of infinite family of multiplications, and they satisfy certain axioms. One can also consider intertwining operators between different representations. And it turns out that this representation, affinization of representations of affinely algebras just have structure of vertex operator algebra and models. And it's precisely the full list of irreducible representation of so-called vacuum vertex operator algebra, which gives the full set. So, then the structure of vertex operator algebra and representations kind of can be encoded into correlation functions of intertwining vertex operators. And they satisfy Knyzhnik's homologic of equation, so that I wrote a book about this with my former students, Etengov and Kirillov. It will appear again later on. So this equation contains, even for SL2, a lot of facts about hypergeometric functions. And eventually, they lead to certain tensor category of representations. So this is previous. All right, so that's about affinization program. And next program that I want to talk is so-called Q deformation program. It appeared about 1985. And it was again started from Serre's paper and Serre's relations that they were transformed Q-deformed in a remarkable way by Drinfeld and Jimbo independently, and that was gave rise to a quantum group. So, however, again, this was kind of culmination point after which the program was developed but the previous results for SL2 already were known for several years by Kulish and Reshetikhin, and also for JLN, Fadeev and his collaborators knew quite a lot about JLN case. So, but then again, after work of Drinfeld and Jimbo, it became clear that the whole program exists. And for example, Q deformation of Schur-Weyl duality, which is our kind of bread and butter, so was done by Jimbo, and that was a beautiful result. But then it was a question about Clifford-Weyl algebras. And after that, you can get Q disease, as it was called at that time, and you can do everything, and you can Q deform anything that you know, like Q superalgebras, Q octonions, Q Jordan algebras. All you need is Q deformed tensor category, and then use small representations and find corresponding Q version of this, and you get all the right formulas. But again, you get a lot of unexpected new structures. So one of them was actually two main such things. So one is three-dimensional topological field theory by Witt and Reshetikhin Turaev, and another is existence of canonical bases by George Lustig and Kashibara, and also structure of these algebras at roots of unities. Certainly, I also got this Q disease at some point, but at least for some period of time. And I wrote several papers. One of them was related to the graphical calculus of Penrose-Kaufman, which is just allows some combinatorial explanation of tensor category in the case of SL2. So essentially, and I wrote a paper with my former student Khabanov on canonical basis, actually on dual canonical basis and this tensor products. So it turns out that dimension of this invariance of tensor products equal to all possible pictures of non-intersecting edges with number of vertices on n-gons equal to lambda 1, lambda 2, lambda 3, which are parameters of representations. So, and then there is a rule to glue two such n-gons and eliminate intermediate H, which is so-called Jones-Wenzel projection, and you get a tensor category of representations. So, so therefore, we have two kind of programs in representation theory, but it turned out that they're essentially the same. So, and that's the next. Then I'm always more involved. Yes, so they are the same in the sense that tensor category are equivalent. So objects are extremely different. I mean, in affine algebras, representations infinite dimensional, while in quantum groups they're finite dimensional. But as soon as you consider tensor category, so all the structure coefficient coincide when K and Q kind of correspond according to this formula. So this was done by many people. I mean, everybody tried to add something new, like Drinfeld and Kono were one of the first, and then Kashdan Lustig wrote several extensive papers. I also contributed a little bit with the paper of Kirillov and Vachenko in the SL2 case, where I kind of, no, this is, just a second, where we reinterpreted this picture, which is pure combinatorial for quantum group, for affine Lie algebras. It represents certain set of monodromies. And since they match together, since they match together, you get equivalence of these categories very explicitly in the SL2 case. So roughly speaking, the idea of this equivalence that if you erase all the complex structure in vertex operator algebra tensor category and leave topological structure, then you get precisely quantum group tensor category. So, but to make it explicit, it's a bit involved, and many people participated. So, but you can also combine two programs. And this makes it even more powerful. So then you can Q-deform such structures that we've seen before, like vertex operator algebra to Q vertex operator algebra. Kнижник-Zamolodchikov equation to Q Kнижник-Zamolodchikov equation. That what I've done with Rishetikhin, and the talk of Andrei Okunkov was also dedicated partly to quantum Knижник-Zamolodchikov equation. So it's a difference equation. Now, left-hand side is not derivative, but you have certain shift in each of the n variables, Z1, Z2, Zn, and it's a commuting system of equations. And the right-hand side expressed in terms of now R matrices, which satisfy Young-Baxter equation with a parameter. So, and everything worked extremely well. I should also say that Fedya-Smirnov also considered similar equation, and then it reappeared again in K-theory of Nakajima varieties in the work of Andrei Okunkov. So, but we'll come to this later. So at this point, we are now about in 92. So it's another kind of completed period. I would call it infinite dimensional classical representation theory, which includes affine Lie algebras, vertex operator algebras, topological field theories, Knижник-Zamolodchikov equation, and so on. And then what is next? So one could expect that it will be new Lie algebras, new Lie groups, new representation, but it did not happen. So what happened was completely different, and many of you know very well. So that's, now I need a help. Who can return back? Okay. All right. So the next program that I want to discuss is one of my favorite categorification program that we developed with one of Yale postdocs, Louis Crane. It was about 93, form. So original motivation, so we were so impressed with three-dimensional topological field theory of Witten, Reshetikhin, and Turai that we wanted to lift it up to 4 dimensions. So, and the idea is kind of simple. In three-dimensional topological field theory, three-dimensional spaces kind of correspond to numbers, and two-dimensional spaces to vector spaces, and one-dimensional space to category, in particular, tensor category of representation of quantum group. So everything was kind of in our fantasy was promoted one step higher. So numbers become vector spaces, categories, two categories, and this representation category becomes some fantastic two category, which it's even hard to imagine. So the assurance that it's possible was based on canonical basis. So because in canonical basis, all the structure coefficients were positive integers. And therefore, you could start categorify everything, I mean, starting from three-dimensional spaces. And then all the equalities here becomes equivalences there. And equivalences satisfy next level of equalities. And that's what's supposed to give four-dimensional topological field theory. Now, I mean, this idea is well known. So, but at that time, it looks kind of as a big fantasy. And we wrote this paper, which is the only physics paper I wrote, because it's not perfectly rigorous, but contains a lot of conjectures. So then I slowly began to work on this. So first with Havanov, we kind of considered category, I mean, integral structure of tensor product of representation of SL2. And then later on, we were able to do the first step of categorification with Havanov, and also we needed the help of Iosif Bernstein. Then we continued this with Havanov and Katerina Stropel, who proved many conjectures in the first paper. And then I also wrote a paper with Stropel and Sasson. And she gave a plenary talk just a couple years ago, where she explained all these results. I can only briefly say that in order to, so let us consider the simplest possible example when you have tensor product of just two-dimensional representations of quantum SL2. So essentially, it's all encoded into operators E and F, which satisfy the right relation. So in order to categorify this, you can use also representation theory, but more sophisticated one. You need the whole category, BGG category of highest weight models, category O that I mentioned in the classical, in the discussion of classical representation theory. In fact, you just, this category O split it into sum of blocks. And typical regular block has simple object corresponding to symmetric group. But there are also degenerate blocks. And they form certain subcategory. And simple objects in each of these degenerate blocks correspond to, I mean, numerated by binomial coefficients, so a factor of symmetric group, but by a product of two subgroups. So then you can easily compute that sum of all the binomial coefficients equal to 2 to the n, right? So, and that's precisely a kind of dimension of these spaces. So then you can introduce certain functors, because operators becoming functors in categorification. And these functors are the simplest you can imagine. So you just take any representation and multiply it by natural representation or dual to natural representation. Then from these degenerate blocks, you can move to more to general blocks. And you have to project to degenerate blocks again. And that's the definition of functors E and F. And believe it or not, it's at the Grothendieck group level, it's precisely a representation of quantum SL2. So that was one of the first examples. Now there are millions of examples, much more powerful. But at least it was clear that categorification program started. So, and exactly at the same time, so in 1994, another paper appeared, which was actually rigorous, fully rigorous, and this gave rise to another program, geometrization program. So the paper by Nakajima. Again, it was not at the empty place because before Nakajima studied modular spaces of instantons with Kranheimer, and they found amazing kind of relation to certain quiver varieties. So the first quiver varieties in the simplest possible case for ordinary instantons on R4 were obtained by Atiyah, Drinfeld, Hitchin, and Manin in the beginning of 80s. And at that time, it was very big result, I remember. So just fantastic classification of something which cannot be classified. So, and essentially, they reduced the classification of instantons to some linear problem, so about which we can also present in terms of quiver varieties. And that's what was extended by Nakajima to much more general diagrams. So therefore, his key observation is that if you consider this representation of affine Lie algebras and its weight decomposition, then these weight spaces are finite dimensional. And they precisely correspond to cells in some modular spaces of instantons. So that was quite remarkable at that time. So, and this led to this geometrization program. So, in particular, so Nakajima first proved it using some correspondences, and he did not describe directly all the cells in this quiver modular spaces of quiver varieties. So, and I remember I was so amazed with all this structure that I gave it to my student, Alistair Savage, to find the combinatorics. So, and that's what we did. So in the A type, we really studied Nakajima varieties and established all the combinatorics. But it was enormous work, but luckily, maybe more than a half has been done. So it was done by Data, Jimbo, Kuniba, Miwa, and Akada, who studied this affine Lie algebra representations just algebraically, without any geometric realization, because they needed it for two-dimensional statistical mechanics. And we realized that what we are getting from Nakajima varieties is precisely the same combinatorics as they had. And So therefore, I participated a little bit in this geometrization program. But before I go to this, I can say that, again, it happened the same thing as with affinization and Q deformation, that it turned out that they are closely related. The same is geometrization problem and categorification problem. They're also related. So because these spaces were realized as cohomology, or then, as we've heard from Andrea Konkov, as K-theory, but K-theory can be replaced by a regional category of vector bundles or sheaves, so that you can, if you have geometrization, you do have categorification. I mean, it's still very difficult to write everything precisely, but in principle it's done, and that's the relation between two programs. So instead of two programs, we have 4 programs in representation theory. We actually have 2. So, and then what is next? Sorry, again, I'm moving in the direction. So then, yes, so I probably don't have time for this, but you remember we also had extension of classical representation theory when we considered continuous series of representations numerated not by integral points in the positive cone of weight diagram, but by the whole cone. Otherwise, it's kind of the same parameterization. So then you get infinite dimensional representations, which are known as principal series. So, and then it turns out that principal series also admit Q deformation. That is my program number 5. But it's very subtle, because in this case you obtain modular double quantum group, which was originally discovered by Fadeev, studied by Techner, and this is now is developing kind of direction in representation theory. So, and my former student, Ivan Ip, is one of the experts. So we wrote one paper about generalization from SL2, which was done by Fadeev and Techner, to SLN and more general case. And everything works extremely well, but there are some kind of completely new phenomena. Okay. All right, so that's the situation. So categorification and Q deformation, but what about new algebras and new representations? So when I gave a talk a very long time ago at ICM, I already began to talk about this, but at that time it was still far away. So, so the idea is simple. We obviously have this class of affine Lie algebras constructed either via Serre relations using extended Dynkin diagrams, or this realization as loop groups and central extension. So why don't we extend either construction further? So for example, you can take arbitrary quiver, arbitrary diagram, arbitrary Cartan matrix, and then you discover Kac-Moody algebras and complete generality. Or you can replace loop by n-dimensional space and consider maps into Lie algebra. This is known as current algebra. So, but the problem that none of these ideas work. So many years passed, no progress has been achieved. I mean, there are certain papers on general Kac-Moody algebras, but they're not very deep and no interesting theory can be developed. So the same as here, I mean, physicists, especially in the 60s, tried very hard working with current algebras and their representation, but nothing happened. So the Lie algebras are too general to expect deep results. That's what I wrote. Nevertheless, we can consider two simplest classes in both generalizations. And that's my proposal, very, very elementary. So on one hand, you can consider two-dimensional generalization. So just maps from Riemann surfaces into finite dimensional algebra. And second, you can consider so-called overextended Cartan matrices, overextended Dynkin diagrams. And the first leads to complexification program, but it's not complexification of the target, it's complexification of the base, which is much more difficult. And hyperbolization problems. So some results, some highly non-trivial results have been obtained in both directions, and that's what I believe will be the next big step in representation theory. I don't know when it will happen. I mean, some results exist, but there is always a critical point after which there is a big expansion of papers and people working in the area. It did not happen yet. So therefore, let me at least explain why it should be possible. What? 20? Okay, all right. So then I don't need to rush with this. Okay, so the left-hand side represents something that we know extremely well. So first of all, if we talk about coadjoint orbits, they already appeared in relation to Wiener measure, as you know, so we need to describe these orbits. So they follow from so-called Flaquet theory of differential equation with periodic coefficients. And the answer is just maximal torus factored by the Weil group. So they classify this orbits. So then, if you consider central extension of the corresponding groups, loop groups are not enough. So you cannot just write cocycle by any possible formula for topological reasons. So you need to go to 2 dimensions. And when you go into 2 dimensions, whether you like it or not, you have to use the Ram theorem. Actually, this is called also Green theorem 1 and 2, but it's also, you need also 2 and 3 at some point. And because you need some topological term that is present in the construction of central extension. So, and then you discover topological field theory and what is called Witten-Reshetikhin-Turaev theory, John's polynomial, etc. But if you consider the simplest possible invariant, this will be beginning of 19th century, Gauss linking of 2 circles, say C1 and C2. So it can be computed using this 3-dimensional integral, but it also can be expressed combinatorially. So instead of 1 circle, you can just consider the disk and consider number of intersections with the right directions with the second circle. And then you get calculation of this integral, which is also Gauss linking, right? So that's the simplest possible that you can imagine, but still non-trivial. So you can try to generalize all of this for the Riemann surface. So first of all, when you consider orbits, you immediately realize that you are dealing with vector bundles or principal G bundles on this Riemann surface. So which is well-known kind of structure which is used again and again. So, and then you need construct central extension. So it turns out that the central extension is given by the Jacobian of the Riemann surface. So this we established with Ettinghoff kind of in some abstract way. But with Hessin, I was able to do it explicitly. So the difficulty was that if you consider Riemann surface, and for example, like torus, so it's not a boundary of something simply connected, just impossible. So there is no topological solution to this problem. But there is complex solution. So, and this is what we called the Ramley-Ray theorem. So it's our great discovery. I mean, in reality, every expert knows this, but it's not written in the first page of the book on complex analysis. So what happens is the following, that you can consider a Riemann surface and put it into two-dimensional complex space, which is also four-dimensional real. And then you have this amazing identity where alpha is again like in the de Rham theorem, and theta, this holomorphic one form on the Riemann surface. And you can lift it up to some big theta, so that small theta is a residue of the large theta, and this residue is known as Leray residue. So therefore, you get this identity, which is called, which we call de Rham-Leray identity. With the help of this identity, you can repeat the construction of central extension 1 to 1, and then you get the group. So, and also about three-dimensional invariants, you have analog of Gauss linking number, and this becomes holomorphic linking. So it's independent on metric, but still depends on the complex structure. So therefore, analogy is kind of very strong, but this is yes, but there is no breakthrough yet in this program. And the problem comes from here. So when you consider representation theory, then it's not enough in the classical theory to have real structures. You need complex numbers. I mean, because the main structure that we are using is polarization of functions on the circle into analytic and anti-analytic, into chiral and anti-chiral part. I mean, that's half of all the constructions that we are doing in the case of loop groups. So, but in the complexification, we have to move from complex numbers to quaternions, and that's all the difficulty comes here. So we need to use hyperkähler structure on these maps to construct representation, but I have no idea how to do it. But you can try with exercises. So if you consider complex simple group factored by maximal torus, complex maximal torus, so it has hyperkähler structure thanks to Kronheimer, and the same as with loops into complex group factored by complex group. So it was done by Donaldson. So this is the exercise before you go into construction of representation here. So for example, concrete question is how to recover V lambda and V lambda hat representation of fine dimensional groups and affine groups using hyperkähler structure instead of Kähler structure. So you need some kind of hyperkähler Borel-Weil theorem. So that might be not very difficult problem. So, but also Kähler structure is obviously related to complex analysis. So you go back and forth. And the simplest thing that you have in complex analysis is Cauchy theorem. So in the complexification, you need quaternionic analysis. However, as complex analysis exists, I mean, you can write several thousand pages on this. And quaternionic analysis more or less finished after 20 pages. So it's practically doesn't exist, but it's not empty. And the question, I mean, whether one can develop and use quaternionic analysis to construct this representation. So I wrote some papers with Matvey Libin, who was a postdoc at Yale, and we found some interesting relation to Feynman diagrams and some possible connection with four-dimensional conformal field theory, but still it's not fully developed. So on the other hand, what we've heard today from Arakawa, so that four-dimensional quantum field theory already beginning to appear in relation to, I mean, to vertex operator algebras and structures that we know. So therefore, it might be that the complexification problem will be flourishing very soon. So, but still, it's a preliminary stage. And then finally, hyperbolization program. So this is based on the idea that you consider overextended Denkin diagram. So you add to 0 -1 point. So this sounds extremely naive, but it turns out that that the corresponding algebras can be analyzed sufficiently explicitly. So what I can say? I mean, it's still a major problem of geometric realization of the corresponding Kac-Moody algebra. So some people believe that its symmetries of gravity and supergravity, etc., but it's never been proven. So I hear this from physicists during the last 40 years, and they continue to write papers about this, but it's still not a mathematical area. So, but elementary things we can do. So I wrote some papers about, for example, Weil group, and it's remarkable that when r equal to 1, so that picture is like this, that the Weil group is modular group. So this you can figure out in 2 minutes. But first, when we observed it, it was quite exciting. So, but this actually works further. For A2, you just have to consider Eisenstein integers. So modular group of Eisenstein integers. And even for E8, you still have this matrices 2 by 2, but over octavions, which are some integral structure inside octonions. So returning back to SL2, quadratic, weight lattice is nothing else but quadratic forms. And that's what was developed by people like Gauss in beginning of 19th century. So therefore, kind of Cartan path looks nice. But if you consider grading with respect to new point, you also have some nice surprises. So 0 path in this decomposition is certainly a finely algebra itself. But the first and minus first component tends to be the simplest possible representation called basic representation of a finely algebra. So, and And this decomposition, so we know also a little bit about other pieces, but we still cannot collect it into beautiful geometric picture of this hyperbolic Kac-Moody algebra. So, but nevertheless, it was noticed that multiplicity weights for any alpha is given, upper bound is given by partition function of R colors, where R is rank of Cartan. But when R is 1, it's just ordinary partition function, so correspond to SL2. Nobody can prove it. So this is still open problem. All the computer calculations show that this is true, up to any number, because we do not have enough tools to work with these algebras. For R4, this is proven thanks to string theory, so and no-go theory. So, but it's very subtle upper bound. So Katz and Moody and Wakimoto wrote a paper that for E8 double hat, it doesn't work, but it's still open for A-type. And the most interesting is R1. So third observation is relation to theory of automorphic form that we found first in a paper with Feingold, but after that it was developed by Borchers, who defined generalized Kac-Moody algebras, which are also called sometimes Borchers algebras. And so he was able to extend Kac-Moody algebras to big algebras which have better behavior with modular behavior. This was developed further by Gritsenko and Nikulin, and some denominator formula has been formulated for these extensions. So therefore, it's clearly the corresponding kind of character part is SP4Z modular forms, based on SP4Z modular forms. So we are moving to some number theory. But again, probably the right object is right in between and might have the multiplicity given by the conjecture, but it's still open question. On the other hand, there are physics observations. So they go back to Bielawski, Khalatnikov, and Lifshitz paper about relation of Einstein equation and billiards, which were extended by Damour, Henault, and Nicolai. So that they realized that if you consider the corresponding kind of Einstein equation, so then you get billiard in fundamental domain. So in particular for type A, you have d-dimensional gravity, where d is related to the rank of the finite dimensional algebra with shift by 3. So that if R is 1, we can compute that d is equal to 4. So therefore Einstein, I mean real Einstein gravity in 4 dimensions correspond exactly to SL2. So it's as the best we could have. But if you consider E8, you have to add 1 plus 7. And 7 plus 4 gives you 11. So this gives you the dimension, critical dimension of M series. So there are some kind of indication that there is a relation. There are some physics papers about this. So, and then it's question about representation theory of this overextended algebras and possibly kind of Borchers algebras. So again, there are some indications of some fantastic relations between zeta functions and quantum gravity, etc. But this kind of program still waits somebody who will make some crucial breakthrough so that it becomes available for many other people. Okay, so so we combine this in this diagram. So classical representation theory is, as I said, simple Lie groups find dimensional representations, maybe some extension. So it's something before 1967. So then infinite dimensional classical representation theory, which includes affinization and Q deformation, and more or less it crystallized in 1992, and still it's our kind of fantastic achievement. So since 1967 until 1992, and it's kind of golden font of representation theory. And then two arrows. So the modern infinite dimensional representation theory went into this left direction. So this is categorification and geometrization, which is very actively developing today. And there are still many problems and many people working on this. And that is my proposal. So infinite future representation theory. So two major directions, and I do not see any other, unfortunately. So therefore, one of those has to appear in the next 2, 5, 10, 50 years. So it's what I call future representation theory, and it's programs of complexification and hyperbolization. All right, so if you think that it's a very, very hard program, you can compare it with, with this. All right, thank you.
Questions?
Yes. What is what? P? This? Partition. Yes. This is partition of R colors. Sorry, I was a little bit fast sometimes and I could miss some definitions. Yes, so when R is equal to 1, you get just ordinary partition function. And this is upper bound, which is achieved, always achieved because of the basic representation here, which have multiplicity given by partition function of R colors. But the remarkable situation that it's computer shows that it's upper bound. Exactly. But for E8, it's not. For E8, E7, E6, I believe it's not true. So then it adds even more mystery. But for A, it's still true. So there are some computer calculation for A2, which also show that it's correct.
So it's P on the all color.
Our color partition. Yes, that's right. So you can compute this multiplicity using quiver varieties, but the problem, it doesn't help so much to solve these problems. So the quiver varieties is this overextended. That's the quiver varieties of overextended algebras. So with the additional -1 vertex.
So where do you put the additional? What is the pattern to add an extra vertex?
as extra vertex. So I just put it. So first of all, the signature of the corresponding Cartan algebra becomes N1. So it's Lorentzian. And sometimes this algebra is called Lorentzian. So why not anything else? Maybe nobody tried, but there is a physics literature about this algebras, and also Weyl groups were identified in this case. So everything related to Cartan subalgebra, Weyl group, root system. So this is all can be identified without much problem. But if you want the whole algebra, nobody knows how it looks like. So we know something about representations, but we don't know about geometry.
So I have a question, first question about the complexification program. Can you, is there for homogeneous curve, homogeneous surface, is there a well-behaved notion of weights and roots? And in that case?
So you're talking about complexification?
Yeah. For the homogeneous surface.
Yes. So
maybe one previous page.
Yes.
Yeah. So is there?
So here I consider for simplicity just the closed case. I could add punctures as well.
Yeah, closed is good.
And in principle, probably these algebras can be also glued from some basic algebras like pens. So that it's more natural to consider not individual algebra, but just family of algebras. So, but so what is the question? So as I said, in this case, when we consider central extension, it's given by Jacobian. Otherwise, you have to take into account punctures.
Right.
So if you have no punctures and G is 0, then nothing happens. No central extension. And no representation theory probably.
Yeah.
So, but the first case, genus 1 or 3 punctured sphere.
But higher genus, do you have, say, weights and roots, like the usual thing in the algebra?
Weights and roots. I see. So I did not study it to suggest anything.
Sorry, maybe the second question about, you say the hyperbolization program, you said the Weyl group of A1 hat is a PGL2Z?
Yes.
And I mean, that's a complex reflection group. I mean, is that related or just a coincidence?
Is it? No.
I mean, I just say it's a free product, ZIMO2 and ZIMO3.
So PGL2Z, it contains modular group, which is positive part of the Weyl group.
Right.
So you can realize it any way you like. Yes. So it's a Coxeter group. So you have 3 generators and relations according to this overextended diagram.
So do you expect? Do you expect in general it's a Coxeter group, or is it just a coincidence in this case?
That it's Coxeter. So that's what I can show. That, for example, if you take A2, it's Gaussian, not Gaussian, Eisenstein integers. For B2, C2, it's Gaussian integers. PGL2 over Gaussian integers. And even if you consider E8, it's 2 by 2 matrices, but over octonions, so that you have to take integral lattice in octonions called octavians. So therefore, modular group is present everywhere somehow. So, but this is extremely elementary part of the full structure. So, but also, I mean, it's beautiful. For example, Legendre result about classification of quadratic forms up to modular group. That's precisely classification of orders. So it's kind of nice, but it's very elementary. But as soon as you want to do something non-elementary, so then you have to kind of open up the whole program.
Okay. Yeah, thank you very much.
Excuse me. So what is this welcome for D type and also status of conjecture for D type?
For D type, for D4, it's PGL2 over integral quaternions, for example, for D4. So, I mean, you can play with this quite a lot at the level of Cartan.
How about the conjecture for D type?
For D4, that's a good question. Yes, so I have no conjecture. I take my conjecture back because for E8, Katsmudi and Wakimoto kind of found the counterexample. So for D, it might be just exactly right. I don't know. But for A, it seems correct. And but I'll be completely happy to see a proof for A1, for SL2.
So you didn't mention about Nichols algebra.